We're going to do integration involving partial fraction decomposition. Suppose we want to integrate a messy rational function like the integral of 13x plus 3 all over 2x squared minus 5x minus 12 dx. We want to reach into our integration toolkit and think about what strategy we might try. Well, we might try to do u substitution, where I let u be the entire denominator, and the derivative would be 4x minus 5. But the numerator is not a multiple of 4x minus 5, so that doesn't appeal to us. Now, we might try to factor the denominator, but we can also tell that the factors wouldn't cancel with the numerator, so that's not necessarily the strategy I want to go to factor and cancel. But here's what we do want to do. We do want to factor because we can use algebra to rewrite it, the integrand, as two separate rational functions. So we would factor the denominator, and each of those factors are going to become the denominators of their own separate rational expressions that are nicer and easier to integrate. The procedure I'm describing of starting with a rational expression and writing it as a sum of two or more rational terms with simpler denominators is called partial fraction decomposition. And each of those rational terms is called a partial fraction. Now, before we get started on examples, to find a partial fraction decomposition, we need a proper rational function. So a proper rational function, some p of x over q of x, where q of x is non-zero, it has a polynomial in the numerator and denominator, but the polynomial in the numerator has to have a degree that's less than the degree of the denominator. So this is x to the first, and this is x squared. So this is a proper rational function. The degree of p of x, the numerator, is less than the degree of q of x. If the degree of p of x, the numerator, is greater than or even equal to the degree of q of x, we have an improper rational function. And what we need to do is try long division. Here we have the integral of that same messy rational expression, and we're going to talk about how we get to those partial fractions. But just a note, because this process can be long and time-consuming, I am going to shorten a lot of the algebra. So I'm going to jump straight to factorizations. If you need to review how to factor, please go ahead and see review videos. And a lot of the arithmetic is just going to be skipped over. We're going to focus on the process of the partial fraction decomposition and then the integration. So here the first step is to factor the denominator if it's not already factored. So our denominator will be the quantity 2x plus 3 times the quantity x minus 4. And those are distinct linear factors. So each one is going to get its own partial fraction with a generic constant in the numerator. So we'd have sum a over 2x plus 3 plus sum b over x minus 4. So our job is now to find the values of a and b. So the idea is this rational expression must be equal to the sum of these two rational expressions. So this is what we're going to focus on to solve for a and b. We're going to start by trying to put these two back together by finding common denominators. So we need to multiply the top and bottom over here by x minus 4, because that's basically like multiplying by 1, and then multiply this side by the quantity 2x plus 3 on the top and bottom. So now these two have common denominators, so we can just add across the numerator. So now we have one rational expression, a times the quantity x minus 4 plus b times the quantity 2x plus 3, all in the numerator. So now the two denominators are the same, and so the two numerators must be equal to each other if these two quantities are to be equal. So we're going to focus on setting the two numerators equal to each other and ignoring the denominators. The first method we're going to look at is forming a system of equations, which is the tried and true method when finding a partial fraction decomposition, but it can be kind of time consuming. The idea is that we're going to look at the coefficients on the left that are in front of x and think about the fact that if the left side is truly equal to the right side, the coefficient in front of x on the left must equal the coefficients in front of x on the right. Now, we could distribute out a and b to see more clearly what those coefficients in front of x will be. So on the left, we can see the coefficient in front of x was 13, And now after distribution on the right, we have an a in front of x and a plus 2b. That's going to give us our first equation in our system of equations. So in front of all of our x terms, I have 13 equals a plus 2b. And now we're going to focus on the constant terms. So positive 3 on the left must be equal to the constant terms on the right, which are negative 4a and plus 3b. Those do not have x's behind them. So we are going to have a second equation, which is 3 is equal to negative 4a plus 3b. Because it was distributed out, it was kind of easier to see, but it wouldn't have been too bad to just think about the constant term by distributing in a, negative 4a, distributing in b, positive 3b. So now here is my system of equations. And to solve a system, I can either use substitution or elimination. I'm going to use substitution. I'm going to solve this first equation for a. So just subtract 2b to the other side, and then substitute this a into the other equation. Once I substitute that 13 minus 2b into a, and then combine like terms and solve for b, I get b is equal to 5. Then I can plug b equals 5 into this equation that's already solved for a, or really any of the equations, to solve for a. So we get a is equal to 3 and b is equal to 5. Now we go back and substitute those into our partial fractions. So we come back up here and we go ahead and replace a with 3 and b with 5. And now we can integrate each one of these separately, and these have nice general antiderivatives. So this part, 2x plus 3, has a slope of 2, so we're going to need a 1/2 in the front of this integral. So we're going to have the 3 times 1/2 the natural log of the absolute value of 2x plus 3, and then here plus 5 times the natural log of the absolute value of x minus 4. So we have 3/2 natural log absolute value of 2x plus 3 plus 5 natural log absolute value of x minus 4 plus c. But before moving on, we're going to go back and learn one more method for finding those values of 3 and 5 that can be a little bit quicker. All right, so the second method that we're going to use doesn't really have a name, but what we're going to do is we're going to choose x values to zero out terms. So we go back to that original equation involving the numerators, and instead of thinking about distributing in a and b, what we're going to do instead is we're going to look at the terms on the right one at a time, and we're going to think about what is the x value that is going to zero out this term. And this one's a pretty easy one. I can look at the factor x minus 4 and think about what do I substitute in to make this 0? Well, positive 4. Really what we're asking you to do is solve this expression equal to 0. So if I set x minus 4 equal to 0, I get x equals 4. So we're going to take that value, x equals 4, and we're going to substitute it into this equation into each x. So if this is truly an equation, we should be able to substitute any x value in the right and left, and it should still be equal. Well, if we now plug in 4, with a 4 in each x, we can see that this whole term is going to zero out. So the left side adds to 55, this was 0, this adds to 11, and solving for b, we get b is equal to 5. All right, now let's go ahead and try to solve for a. We're going to need to try to zero out the term involving b. So we're going to choose the x value that zeroes out this factor. Well, this one here might not be as easy to do in our head, but what we're really doing is setting this equal to 0. So I would subtract the 3 and divide by 2. So the number that we're going to substitute in is negative 3 over 2 into each x. So here I've substituted negative 3 over 2 into each of the x's. It is a little bit of fractions, but not too bad. So over here, the b value, I just want us to notice that it is going to zero out. 2 divided by 2 is going to cancel and be 1, and then negative 3 plus 3 is 0. So the whole b term is gone. And so now we're just simplifying right here. So we have Negative 39 over 2 plus 3, that's negative 33 over 2. Negative 3 over 2 minus 4 is negative 11 over 2. And so when we multiply by the reciprocal, 2 over 11, the negatives cancel, the 2's cancel. 33 divided by 11 is just 3. So there was a bit of arithmetic involved here to find the value of A is 3 and the value of B is 5. We already knew those were the right answers using a system of equations, but this method can be pretty quick and easy. It just depends on the number that we substitute in to zero out the terms. One more thing, there's actually another method called the cover-up method that aims to be really efficient about finding the values of A and B, also using a lot of mental math. I cover this topic in another YouTube video that you can go ahead and check out if you're interested. In this next example, we have the integral of the rational expression x squared minus x minus 21 all over 2x cubed minus x squared plus 8x minus 4. This is a proper rational function. The degree of the numerator is less than the degree of the denominator, so we're going to try partial fraction decomposition. The denominator does factor if we use factor by grouping, so we're going to end up with the quantity 2x minus 1 in the denominator times the quantity x squared plus 4. The first factor is a distinct linear factor, but the second factor is a quadratic that cannot be factored any further over the real numbers. It's the sum of squares. So this partial fraction decomposition is going to look a little different than the previous one. Any distinct linear factor, 2x minus 1, is going to get a generic constant on top like a. But an irreducible quadratic, like x squared plus 4, is going to get a generic linear function on top, like bx plus c. So now we need to solve for the missing values of a, b, and c. We're going to use the same strategy as last time. Think about putting this back together as one rational expression with one common denominator. So it's like we multiply the top and bottom here by x squared plus 4, and the top and bottom here by that 2x minus 1. And so now we're going to get that equation that we're going to focus on, which is setting the numerators equal to each other. So setting the original numerator equal to each other, and then this one that we just found involving a, b, and c. All right, here's that primary equation that we're going to be focusing on. And we could jump straight to setting up a system of equations, but I am going to attempt to use the method where we choose an x value to zero out a term. We can only do that on the linear factor. So there's no real number I can choose for x here to substitute in and zero out this whole term. But I can let x equal positive 1/2, and that will zero out this entire term right here and allow us to solve for a. So if I go ahead and let x equal positive 1/2, and I substitute that into each x, well, I'm not going to bother plugging it into this term on the far right. We know that's going to zero out. Plugging it in everywhere else, we are going to have to do some arithmetic that forces us to have some common denominators here, but we are going to be able to solve for a, and we're going to get a nice value out. We're going to get a is equal to -5. So we still have to find the missing values of b and c, and we are going to move forward with setting up a system of equations, but already having one of the values is going to make our system of equations really nice to solve. So we're just going to hold on to a equals -5 off to the side as we form our system of equations. Now on this one, I'm not going to actually do the work of distributing out. I'm just going to try to do mental math to think about matching up the coefficients in front of each variable type. So what's going on in front of x squared? Well, on the left side, I have a 1 in front of x squared. And on the right side, if I think about distributing in this a, that will be in front of x squared. And then over here, bx times 2x would give me 2bx squared. So 2b is going to be in front of x squared on the right. Now, if I keep distributing over here, bx times -1 is -bx, not x squared. 2cx is the middle term, that's not an x squared. And then c times -1 is -c, that's a constant. So there's no other terms on the right that involve x squared. So here's my equation for x squared. But notice that since I already have the value of a is equal to -5, I can go straight into solving for the value of b here. So if I plug in -5 for a, I can add it to the left side and then divide by 2 and get the value of b is equal to 3. So now all I need to do is find the value of c. And if I go in and take a look, the value of c over here, if I think about the way I was distributing, I know that -c is going to be a constant on the right-hand side. So I don't even really need to set up the equation for the coefficients in front of x. I can just go ahead and move on and think about what are the constants on the left and on the right-hand side. So on the left side, the constant is -21. On the right side, if I distribute in the a to 4, I'm going to get 4a that doesn't have any x's. So 4a is a constant piece on the right. And the only constant here is the c times -1, so minus c, because the middle terms when distributing on the right side will have x's in them. So here's an equation that only has a in it, and I know the value of a, so I can solve for the missing value of c. Here I substitute in -5 and then add 20 to the left. I get -1 equals -c, so c is equal to -1. So I have all of my missing constants a, b, and c to substitute back into my partial fraction decomposition. Here are my two partial fractions. I'll go ahead and replace a with -5, b with 3, and c with 1. And so now our job is to integrate this. Well, this first term is similar to the previous example. It's going to become a natural log. This one, we're actually going to have to split up. So I'm going to go ahead and split up the second integral. We're going to have 3x over x squared plus 4 plus 1 over x squared plus 4. And now the integral on the left, the integral on the right, we can go straight to an answer. So the one on the right is going to become an arctangent. So let's go ahead and evaluate those two. So we're going to have -5 over 2, because a 1/2 is going to come out here. And then the natural log of absolute value of 2x minus 1. And then the integral of 1 over x squared plus 4 is going to be 1 over 2 arctangent, or tan inverse, of x over 2. And then we still have this integral in the middle that I haven't yet solved, 3x over x squared plus 4 dx. And of course, there is going to be a plus c in the back. We won't forget about that. But this integral in the middle, we want to do with a u substitution. So we can go ahead and, let's say, let u be x squared plus 4. Then du is 2x dx. We have a 3x dx, so I'll just divide over the 2. So a half du is x dx. So this middle integral is going to be 1/2 the integral of du. Actually, I don't want to forget about that 3. I had to pull that out. 3 times 1/2 du over u. So we'll have 3/2 the natural log of u, but u was x squared plus 4. And then we'll just go ahead and bring down the rest of the pieces to get our final answer here. So what often happens is that each of the pieces of partial fractions becomes a natural log type of function or an arctangent type of function. So these are very common pieces to end up with when you start with the partial fraction decomposition. All right, in this example, we want to integrate 3x cubed minus 18x squared plus 29x minus 4 all over the quantity x plus 1 times the quantity x minus 2 cubed dx. Now, lucky for us, the denominator is already factored. We have one distinct linear factor, x plus 1, but we have a repeated linear factor, x minus 1 cubed. So that's going to give us a different looking partial fraction setup. So we're going to have a generic constant over x plus 1, but the repeated linear term, x minus 1 cubed, is going to give us 3 different partial fractions. I'm going to have a generic constant over just x minus 2, another generic constant over x minus 2 squared, and a final generic constant over x minus 2 cubed. So now I need to solve for a, b, c, and d. And we are still going to want to think about putting this back together to be one rational expression with this original denominator as our common denominator. Let's go ahead and talk through what our big numerator is going to end up being. So right here, I have a over x plus 1. If I want this to have a denominator of x plus 1 times x minus 2 cubed, well, this is missing an x minus 2 cubed. So the numerator on the left here is going to be a times the quantity x minus 2 cubed. And then the second piece of the numerator is going to have b times, okay, well, this denominator has only one copy of x minus 2. It needs an x plus 1, so the top and bottom need an x plus 1. And it needs 2 extra copies of x minus 2. There's only one copy on the bottom. I'd have to put 2 more, so I need 2 more on the top. So I'm going to have x minus 2 squared. This third term, if I'm going to make this have a denominator of x plus 1, x minus 2 cubed, it's also missing an x plus 1. So we're going to have c times the quantity x plus 1. And then it has 2 copies of x minus 2. It's missing one more. So I would need the top and bottom to get multiplied by 1 extra copy, of x minus 2. And then finally, the last part of the numerator here has that plus d, and the only thing this is missing is a copy of x plus 1. So if I go ahead and multiply that last part by x plus 1, now I have my numerator here that has my a, b, c, and d that I'm going to set equal to the original numerator at the beginning of the problem. So it's going to look like this big thing that we're going to use to find those missing values. Now here's our big equation, and we generally want to avoid going straight to a system of equations if we can help it. And even though we had a repeated linear term, we can still use the method of choosing an x value to zero out all but one term on the right-hand side. The first value that I'm going to choose is to let x equal 2, because plugging in x equals 2 will zero out this first term, this second term, because this piece right here would be 0 and this is all multiplied, and this third term because it also has an x minus 2, so 2 minus 2 is 0, and this whole thing would multiply to be 0. So we're going to substitute in x equals 2, and all 3 of these terms will zero out, and I'll be able to solve for the value of d. So if I let x equal 2, plug 2 into each x on the left, and then again, all of these terms are gone, so I just plug 2 into this x in this final term, and if I do the arithmetic, I end up getting d is equal to 2. Going back to this original equation, I can also let x equal -1, and that's going to zero out the last 3 terms because they all have a factor of x plus 1. So now here's the work for letting x equal -1 into each x on the left, and then into the first term on the right because all the remaining terms are just 0. So after doing the arithmetic on the left and right, we end up getting the a value is also 2. Now, unfortunately, we can't zero out all but one term anymore. There's no remaining x values that I can use that to find b and c. So we are going to go ahead and start to set up the pieces of a system of equation that we would need to find b and c. Here's our main equation, and here are the values we worked for. We already know a and d. So let's think about what parts of a system of equation we can set up that aren't going to be a lot of arithmetic here. So if I think about the first term on the left, 3x cubed, the coefficient in front of x cubed is just 3. And on the right-hand side, it's actually not going to be too bad to think about what's going to be in front of x cubed. Now, x minus 2 cubed, I don't want to have to multiply all of that out, but I don't have to. If I think about doing all that distributing, the leading term is going to be just x cubed, and then we're going to multiply an a by that. So if I think about the stuff in front of x cubed on the left, that was just 3. And so far on the right, we're going to have an a in front of x cubed, if I think about multiplying all of this out. Now, from the second term, if I think about multiplying out x minus 2 squared, the leading term from that piece alone will be x squared, and then some other terms. And then when I multiply that to x plus 1, x squared times x is going to give me an x cubed. So this second term will have an x cubed, but the only thing that's going to be in front of it is a b. So we're going to have a plus b, but the remaining two terms don't have an x cubed involved. So x times x is just x squared, and then here I just have an x to the first. So my equation that involves the coefficients in front of x cubed is just 3 equals a plus b, and a is 2. So we can solve for b right away. We get 3 equals 2 plus b, so b is equal to 1. Now, the only value we're missing is c. We want to go ahead and set up another part of our system of equations, but one that isn't too hard to work for. So we set up the one involving x cubed, the x to the highest power here, and we're actually going to skip over the middle two terms. Those are going to be a lot harder to find what's in front of x squared and x because, again, of the multiplication going on here. But the constant setup is not going to be too bad. So on the left, the constant is -4. And on the right-hand side, if I think about multiplying out x minus 2 cubed, the only constant, the one that's not going to have any x's, is going to be -2 cubed. So -2 cubed is -8, and then it's multiplied by a. So I'm going to have -8a plus, now from the second term, if I think about x minus 2 squared, when I distribute all that out, the last two terms is going to be -2 times -2, or -2 squared. That's 4, positive 4. Well, that would get multiplied by the 1, which is just still positive 4, and then eventually the b would distribute in. So the constant from this second term is just 4b. Now, from this one here, it's a lot easier to think about. If I distribute, the last terms form the constant. 1 times -2 is -2 times c. So -2c or -2c is the next part of that equation. And then finally here, even easier, I have dx plus d. So the only one that doesn't involve x is going to be plus d. And if you need more convincing about these two, I mean, take a minute to actually distribute it out and convince yourself of the fact that these are going to be the constant values. And so now we're only missing c. We have the values of a, b, and d. Let's go ahead and substitute them in to solve for c. After substituting in those values, I end up getting a c value equal to -3. With all of our missing values now, we can substitute them back into the partial fraction decomposition. Let's not lose sight of the original problem. These were our original partial fractions, so now let's substitute in the values of a, b, c, and d. And now think about integrating each one. The first two are going to become natural log functions. So we're going to have 2, the natural log absolute value of x plus 1, plus natural log absolute value of x minus 2. The next two terms, I actually want to think about them as, let's say, -3 x minus 2 to the -2, and then 2 times x minus 2 to the -3. And because the inside is linear, we can just do the power rule for integrals here, thinking about how 1 over the slope would come out of this, but the slope is just 1. So it's going to be kind of nice. We can just say this is -3 x minus 2 to the -1, so I'm adding a power, and then dividing by the new power, and then plus 2 times x minus 2 to the -2, so I'm adding 1, and then dividing by the new power. So let's clean these up a little bit. The negatives cancel, and I can bring this expression back down. So I get plus 3 over x minus 2 minus 1 over x minus 2 squared. And then we have the first two terms. So here I have my final answer. And we just want to be careful. We were only able to kind of do this. This was technically a use substitution, but we did it in this manner because the inside is just a nice linear expression with a 1 in front of the x. Now let's integrate 1 over x times the quantity x squared plus 1 all squared dx. So the setup of this one is going to look like the integral of some constant a over the linear. Let's go ahead and do the integral of 1 over x times the quantity x squared plus 1 all squared dx. Here, the denominator is already factored for us. We have a distinct linear term, just x, and then we have a repeated irreducible quadratic. X squared plus 1 can't be factored any further, and it's repeated. So our partial fraction decomposition setup is going to have the following look. We're going to have a generic constant a over x plus generic linear function bx plus c over x squared plus 1 plus another generic linear function dx plus e with different coefficients over quantity x squared plus 1 all squared. So now we need to go ahead and solve for all 5 missing values. We're going to put this back together with the common denominator of the original denominator in the rational expression. So this first numerator here, a, it's going to have to get multiplied by quantity x squared plus 1 squared because the denominator doesn't have any of those. So we're going to have a times the quantity x squared plus 1 squared plus now this middle numerator here is going to have to get multiplied by an x because this denominator is missing this factor of x, and then another factor of x squared plus 1. So we're going to have bx plus c times x squared plus 1. And then now, oh, I didn't give myself enough space. So the last part is going to have to get multiplied by an extra copy of x. So we have dx plus e, and it already has 2 copies of x squared plus 1. It's just missing the x. Okay, so now this entire numerator has to equal the original numerator 1. Here is the equation that I'm going to be working with, and I am going to go ahead and start by letting x equal 0. That will zero out these 2 terms here. So if I let this x be 0 and this x be 0, these 2 terms will zero out, and then I can solve for the value of a. All right, so in this equation, the left side, I can't substitute in 0, so it just stays 1. All these terms with just an x as a factor zero out, and then 0 squared plus 1 is 1, 1 squared is 1, so a is just equal to 1. Now, there's no value I can substitute into x squared plus 1, this irreducible quadratic, to make it zero out, so we're going to move forward with setting up a system of equations. And unfortunately, we're going to set up the entire system of equations. So we're going to have to think about, what's in front of the coefficients on the left and right. And on the left side, it might not be as intuitive right away because all I see is a 1 to think about what's in front of those powers of x, but it's just 0. So there's a 0 x and a 0x squared. So since there's no x terms on the left, the coefficient over there is just 0. All right, so let's think about on the right-hand side, what is that highest power of x going to be if I multiply things out? So I'm going to multiply out some, but not all, of the terms over here. So on the right-hand side, I'm going to have a times x to the 4th plus 2x squared plus 1. So multiplying out a binomial isn't too difficult to do in our head, right? So we'll do that. And then plus bx plus c. And then here I'll just multiply out x times x squared plus 1. So x cubed plus x. And then here I'm just going to leave this one because I can think about this one in my head. So I'm only going to multiply out sort of what I need to. And then let's kind of go one at a time and think about x to the fourth on the left. Well, okay, there's no x's on the left. So that means all of those coefficients are 0. On the right, what's going to be in front of x to the fourth? Well, just a is going to be in front of x to the fourth right here. So I'm going to have a. And then let's see right here, will there be an x to the fourth? Yes, bx times x cubed is an x to the fourth. And all the remaining terms there when distributing are not going to have an x to the fourth. So just bx to the fourth, so just plus b. And then here, this last one is just a dx squared. So just a plus b. Okay, well, a is equal to 1. So I have 0 equals 1 plus b, so b is equal to -1. Now let's move on to x cubed. Let's think about what's in front of x cubed on both sides. Well, we already said the left side is 0 in front of all those x's. Here, in this first term, there's no x cubes if I look at all the x's, so we can skip over that. Here, that first one was x to the fourth. Here, distributing bx times x, that's x squared, but here, cx cubed, so I have c is in front of x cubed. And then over here, there is no x cubed, just x squared. So c is just equal to 0. So that equation is just one of the values. So we now have a, b, and c. Let's go ahead and think about what's in front of x squared. Okay, on the left, 0. There's no x squared term on the left. On the right, something more interesting. So a times 2x squared means 2a is in front of x squared. Let's see, right here, we said bx times x was bx squared. So we have plus b. There's a b in front of x squared. And then right here, dx times x, so d is in front of x squared. Well, we have the values of a and b, so we can solve for d. So we have 0 equals 2a, a is 1, so just 2, plus the value of b, that's -1, plus d. So that 0 equals 1 plus d, so d is also -1. All right, so we have A, B, C, D. All we're missing is E. So let's think about what's in front of X. Well, on the left, there are no X's, so 0. And then let's see on the right. So A times 1, that's a constant, not an X. Let's see here. This was bx to the fourth, bx squared, cx cubed, cx. So C is in front of X. And then let's see, dx squared plus ex. So c plus e are in front of x on the right-hand side. C was 0. So that must mean e is equal to 0. So if 0 equals 0 plus e, then e is also 0. So we actually have all of our values now. A is 1, b is -1, c is 0, d is -1, and e is 0. So we actually didn't have to find the last one, the constant one, but almost all of them, right? But they weren't too bad to solve, especially since we had one value that we found using a clever choice for x. So let's substitute all of these back in. Here was our original partial fractions, so plugging in a, b, c, d, and e. So the first integral, 1 over x, is going to be natural log absolute value of x. And then the second two integrals we're going to use u substitution on. So here, this middle one, x over x squared plus 1, u will be x squared plus 1. This last one, we have x over quantity x squared plus 1 squared. U will still be x squared plus 1. So I have u is x squared plus 1, du is 2x dx. Both of them have an x dx, so 1/2 du is x dx. So this middle one becomes du over u, but this last one becomes du over u squared. So we have, again, the integral is going to be natural log, but of u this time. And this one is u to the -2, so it's going to be -1 over u. So now it's just a matter of multiplying these negatives and then substituting u back in. So here we end up with our final answer. And so the integration techniques never end up being too bad. Again, a lot of natural log, use substitution, a couple of arctangents in there. It's really the algebra of the partial fraction decomposition. In this problem, I have the integral of x cubed minus 6x squared plus 5x minus 3 all over x squared minus 1 dx. Now, before we think about factoring the denominator, we have to pause and recognize that this is not a proper rational function. The degree of the numerator is bigger than the degree of the denominator. So we're going to start by doing long division. So all the previous examples were proper rational expressions. This is improper. So our long division is going to be dividing x squared minus 1 into x cubed minus 6x squared plus 5x minus 3. And let's recall how this works. We focus on that first term in the divisor, and we think about what do we multiply x squared by to get to x cubed? That's going to be part of the quotient, so just x times x squared is x cubed, and then we multiply x times x squared, that's x cubed, we put it directly under the like term, and then we multiply x times negative 1, which is negative x, and we put it under the like term. And then with division, we subtract these quantities. So we're going to have to make this minus x cubed and then plus x. And what should happen is x cubed minus x cubed cancels and gives us 0. And then we add down here. So this is a 0. So if we add down, we're just bringing down negative 6x squared plus 6x. And then again, we're adding 0 to negative 3. So we just bring down minus 3. And then we do it again. So we think about x squared. And what do I have to multiply x squared by to get negative 6x squared? Well, negative 6. So negative 6 becomes the next part of the quotient. And then we multiply negative 6 times x squared. That's negative 6x squared. Negative 6 times negative 1 is positive 6. But then again, we subtract these. So we change the sign. This becomes plus. This becomes minus. And then again, we add down. So the minus and plus 6x squared will cancel. 6x plus 0 is 6x, and then minus 9. Well, now we wouldn't think about dividing x squared into 6x, so this is the remainder, which goes over the divisor. So the original rational expression is equal to, I'm going to move this over to make some space. So this original problem is equal to x minus 6, so the quotient, plus the remainder, 6x minus 9, over the divisor, x squared minus 1. Now, what's left over here, there happens to be a remainder that's left over, this is now a proper rational expression. So we can do partial fraction decomposition on this piece. So this we can just integrate right away. So the integral of x is x squared over 2. The integral of this minus 6 term is just negative 6x. But then we're integrating 6x minus 9 over, let's factor the denominator, x minus 1, x plus 1. So it's at least going to be a nice one where we have the integral of sum a over x minus 1 plus sum b over x plus 1 dx. And then we bring down our first two terms. So now our job is going to be to find the values of a and b here. So remember, what we want to do is combine this back together, but when it's just two distinct rational denominators, distinct linear denominators, we can really just cross multiply. So we have the original numerator, 6x minus 9, has to be a times x plus 1 plus b times x minus 1. So we want to just be able to go straight to this main equation so that we can find a and b. And for this, I'm going to let x be negative 1 and positive 1 to solve for a and b. So if I let x equal -1. So we'll have -6 minus 9. So we have -15 is equal to b times -2. So -1 minus 1, this part zeroes out. Divide by 2, I get 15 over 2 is equal to b. And then I'm going to let x equal +1. And so 6 minus 9, that's -3, is equal to 2a. So if I plug in +1 here, I get just 2a. So divide by 2, I get a equals -3/2. All right, so now I can go back and plug those in right here to finish solving. All right, so I try to kind of box this scratch work off a little bit. We substitute a and b back in. So here we are back in the problem. And each of these is just going to become a natural log. So we're going to have a final answer of x squared over 2 minus 6x minus 3/2 natural log absolute value of x minus 1 plus 15 over 2 natural log absolute value of x plus 1 plus c. Here we have a definite integral, the integral from 0 to 1 of x squared plus 3x minus 7 all over x squared plus 2x minus 8. Now, just like the last one, this is an improper rational expression because the degree of the numerator is equal to the degree of the denominator. So we need to do long division again. So we're going to divide the denominator x squared plus 2x minus 8 into the numerator x squared plus 3x minus 7. And we're looking at that leading term in the divisor x squared, thinking about what do I have to multiply that by to get x squared, or how do I divide x squared into x squared? Well, it goes in one time. So now I have 1 times x squared, that's x squared. I have 1 times 2x, so plus 2x, and then 1 times -8 is -8. But we subtract all of those quantities or change all of their signs. So we have minus, minus, plus, and the x squared terms cancel. 3x minus 2x is just x. And then -7 plus 8 is a +1. And I'm basically done already because I can't think about dividing x squared into x. So now this integrand becomes the quotient, which is just 1, plus the remainder x plus 1 over the divisor x squared plus 2x minus 8. Now, the first term, 1, I'm getting ahead of myself, the antiderivative is just x. So we could say this is x, and we're evaluating it from 0 to 1. And so we would just plug in 1 and plug in 0. So we would just get 1. That's the first part. But then we still have the integral from 0 to 1 of this proper rational expression, x plus 1 over x squared plus 2x minus 8. So we can factor the denominator here. So we have x plus 1 over quantity x plus 4 times quantity x minus 2. And then let's go ahead and split that up into our partial fractions. So I'm going to pull that work off to the side. I'll have x plus 1 over quantity x plus 4 times quantity x minus 2 be equal to generic constant a over x plus 4 plus generic constant b over x minus 2. We ultimately want to cross multiply these to get that primary equation that we work with. X plus 1 equals a times quantity x minus 2 plus b times quantity x plus 4. And then we'll substitute in 2. And let's try to do some mental math here. So if I substitute in 2, the left side is going to be 2 plus 1, which is 3. And then the right side, the first term zeroes out. And then 2 plus 4 is 6. So I'll have 6b. So I get b is equal to 1/2. And then we'll substitute in -4 to zero out the second term. So -4 plus 1 is -3. that's equal to, if I plug in negative 4 here, negative 4 minus 2 is negative 6, so negative 6a. So I also get 1/2 again is the value of a. So now let's come back over here. I'm integrating from 0 to 1. We have 1/2 over x plus 4 plus 1/2 over x minus 2. Okay, so now the antiderivative of each of these is a natural log function. So we'll bring down the 1, plus we have 1/2 natural log absolute value of x plus 4, plus 1/2 natural log absolute value of x minus 2, evaluated from 0 to 1. All right, let's go ahead and plug in 1 first into each x. So I'm going to leave that 1 there. Then I have 1/2 natural log of 1 plus 4 is 5, plus 1/2 natural log of, so 1 minus 2, that's negative 1, but in absolute value bars, that's positive 1, and natural log of 1 is 0. But I will go ahead and put natural log of 1, but that becomes a 0. And then minus, now I'm going to plug 0 into each x. So if I plug in 0 here, I get 1/2 natural log of 4. And then minus, if I think about distributing the negative, if I plug in 0, I get 0 minus 2, but in absolute value bars, that's positive 2. So 1/2 natural log of 2. Now, as far as simplifying goes, the coefficient in front of all of these natural log pieces is 1/2. So what I did was I factored out that 1/2. And then inside here, I can use some log properties. So since these are all natural log, remember that when I subtract logs with the same base, the ones that are being subtracted, their argument goes to the denominator. So basically what I end up having here is 1 plus 1/2 and then natural log of 5 over 4 times 2, because the argument of each of these goes to the denominator and is multiplied. So I have 1 plus 1/2 natural log of 5/8. So just working through some of that old logarithmic properties stuff. Now, before moving on, I just want to point out one thing. After we did long division and we had x plus 1 over x squared plus 2x minus 8. Since we're in the mindset of partial fraction decomposition, we went straight for that strategy, and that was perfectly fine. But on this particular example, we actually could have used a u substitution. So I'm going to put or. What we could have done is say that u was x squared plus 2x minus 8, then du is 2x plus 2 dx, and if I pull out a 2, I actually have a multiple of the numerator there. So a half du is x plus 1 dx. So I could have done a u substitution. I did have to deal with the limits of integration, but just want to keep that in mind. So sometimes we get fixated on a new strategy and we want to force that to work, but we still have and want to have our toolkit of other strategies to potentially use.